Hello everyone, in this video I'll talk a little bit about the low power modes of the microcontroller that I use in MSP430. So low power modes are very important to reduce the energy consumed by the system. To reduce the energy, there are some ways we can do that. The energy that the system consumes is the integral of the power in time. So from the time 0 to a given time t0. Since power is the multiplication of the voltage times the current, we have a few more degrees of liberty to work with. So we can, for instance, lower the VCC. Our microcontroller, the MSP, works from 1.8 volts to 3.6 volts. We can also lower the current, but that's kind of hard because the static current is already zero. This is a digital system. It uses a MOS transistor, right? But the dynamic current is a function of the frequency, which is controllable. So I can control the frequency and lower the power consumption, which is great. Also, we can lower the time that the microcontroller stays active. So if we change the period of time that the microcontroller is active, we can use the low power modes. That's where they shine. So in the supply voltage range of the microcontroller, here I'm plotting the system frequency in megahertz and the supply voltage of the microcontroller. And there are different modes of operation. Let's say if the supply voltage is not enough, we cannot run the system as fast as the datasheet says. Like for instance, my MSP430 here can work up to 25 megahertz, but that's only when I supply enough voltage for the system. Only if I supply up to 2.4 volts to the system. There is an internal regulator that will control the CPU voltage from 1.4 volts up to 1.9 volts. So you need enough voltage inside the processor so that this linear regulator works, so that it can work fine. So this is quite interesting. So to save power, you can reduce the system frequency. Let's say that your system is supplied with 3.3 volts. So you can run your system up to 25 megahertz, but there is nothing that obliges you to use 25 megahertz. You can lower that frequency up to the frequency that you want. Let's say we want to run it in at 1 megahertz, for instance. So you can do that. The interesting thing here is that the current that is pulled from the microcontroller is a function of the state or a function of the number of peripherals that are turned on. And there is a register on the processor that is called the status register, which we have already seen before when we saw the interrupts. There is a bit that is called the global interrupt enable that allows us to connect the interrupt flags to the processor. But there are 4 bits that control the low power modes of the system. These bits will disconnect or will disable specific clocks of the system, like for instance crystal clocks, the digital oscillator, and the submaster clock. And it can actually turn off the processor itself. So the processor will automatically turn on whenever there is an interrupt. So the idea here is to lower the time that the processor is active. So if the processor is active, it will consume a lot of current. If it's not active, it will consume very low energy. So if we can maximize the time that the processor is on low power mode, we can then save a lot of power. The microcontroller that I use has a lot of low power modes. From low power mode 0 to low power mode 4.5, there are several steps on the way. So in active mode, all of the system clocks are turned on. We have three clocks of the system: a master clock, which is the processor clock, a submaster clock, which is a very fast clock especially used for serial communication, a slow clock, which is an auxiliary clock, a clock, which is mainly used to count time. So low power mode 0 will turn off only the processor clock, the master clock. From this low power mode on, we have different modes that will turn specifically one or another clock, and in between it will turn off the digital oscillator clock. So it's important to know in your application what is the clock that you are actually using in your peripherals to go as aggressive as you can. It's important to note here that low power mode 4 onwards, they are so aggressive, we cannot return from the low power mode. And once we have entered this state, this is like an off state for real. We can only return to execution if we reset the microcontroller. There are intermediate low power modes here. Low power mode 4 can retain data in the RAM, but low power modes 3.5 and 4.5 doesn't retain RAM information. So these are quite aggressive modes. Low power mode 3.5 has this name because it can return from the low power mode to active mode using a specific clock that is called a real-time clock, an RTC, which is a timer with very specific comparators. It's a simpler timer than we've seen before. There are some helpers to enter these low power modes. We can enter low power mode using this macro, low power mode 0 to LPM 0 and onwards up to low power mode 4. To enter low power modes 3.5 and 4.5, we have to actually configure and turn off the voltage of the system by accessing the power management module control register. This is the code that we have to use before turning off the processor. So the idea of low power modes is to lower power consumption. So to conclude this session, this video, I would like to recommend to you guys to use low power modes whenever possible, and choose a low power mode based on the clocks of your system that your system will use. To enter a low power mode, you use the macro low power mode and the number of the low power mode modes that you want to use. You can exit a low power mode during interrupt service routine by running a macro called low power mode off on exit. I don't think it's very interesting to say what's the mechanism behind this execution macro, but this is how we do it. And this is it. Let's now see what are the different paradigms of programming that we can use on nanosatellites.